Okay, my goal for this video is to talk about specific heat and latent heat with a worked example, and I've got some equipment. I'll show it to you in just a minute. I've got a 100-gram chunk of aluminum here. All right, and I'm going to put this in boiling water. Maybe I'll do that right now. I'll get that out in a minute. And so that's going to be in boiling water, so it should rapidly reach 100 degrees Celsius. And we're going to dump that into an ice water bath. So we're placing hot aluminum in ice water. And I want to find the final equilibrium temperature, and at the end of the video, I'll try to talk about real-life considerations. So I've got some numbers up here. Oh, I forgot to write aluminum. Let's get that up there. C, aluminum. Let's use purple for that. So there it is. I'm reading these numbers off a table on page 69. Volume 3, and this number 2. And let's go look at the demo first, because it takes a while to reach equilibrium, and then we'll come back and do the math. All right, and so looks like, I don't know if you can see this or not, but this scale says 219 and change. I'm going to tilt it a little bit. That's obviously going to change the scale reading, but so hopefully you can see that on the screen. You can't at all. Whatever, you just got to trust me. This one's, I measured the mass of the beaker, and this one here is about 620. And now I'm curious how much the ice weighs. So I'm going to go ahead and put a thermometer in here right now. So the thermometer says 22.7. You can't really see the decimal point, but I'm going to stick this one in here. All right, and maybe I'll turn it like this so you can see things a little bit better. So this should start cooling off. And then I need to measure the mass of the ice. So let's do that real quick. I'm going to zero this. Oops, come on, you. Obviously, you can see I'm introducing errors because right now I'm warming up the ice. But it looks like I've got 12.1 grams of ice. All right. So I'm going to write that down on the screen so I don't forget. 12.1 grams of ice. From that, we can figure out the mass of water. And now what I'm going to do, I'm going to find that chunk of aluminum in here. This is boiling water. Can't see anything. Man. Okay, now I can see. All right. Trying to get this thing out of here. Ah! You know what? I'm going to use this hot glove. All right, sorry. This is not perfect. But I'm going to throw this in here, drop it in here, and now mix it a little bit. And so our goal is to find the final equilibrium temperature. Now, one thing I want to mention while I've got this video on here, you'll notice there's still ice and water in here, and this is a complicated system. The temperature is actually different at different points in here. But while the ice is melting, the classic model is to say the temperature of the ice water is still at 0 because you've got ice and water mixed. Now, clearly that's not true at the top and the bottom. But now what I'm going to do is let this come to equilibrium for a while, and I'll leave that here. And let's go do the math, and we'll come back at the end. Let that reach equilibrium. So let's see what we've got here. Oh, this is the mass of the ice water and beaker. So let's do a quick calculation here. If you want to pause the video and try and do this yourself, I will mention this. We're going to try and use these equations that we talked about before. We're going to ignore the calculus and do the approximate values of this and this. And we're going to try, you want to pause the screen and write down those equations. 3, 2, 1, here I go back. Oops. Come on, go back. So what we're going to try and do is use those equations to learn about the final temperature. If you want to try and do it yourself without my help, go for it now. Otherwise, I'm going to proceed in 3, 2, 1. All right, I'm going to get all the masses first. 621.4 minus 219.6. So there's 401 grams total, minus 12.1. It's 389.7. And these masses are probably off in the tenths column because I wasn't taking great care to make sure the balances were leveled and there may be some drips of water on them. So I'm expecting some errors. I'm going to round these here probably. All right. So I'm assuming I'm off. Hopefully I can get this accurate to a gram. And now let's take a look. When you're running these problems, I like to think of it this way. The sum of the Q's equals 0. Now, at first this might seem kind of counterintuitive. What I'm saying is the Q to melt the ice plus the Q to warm the water. After all the ice melts, it's just water and then it can raise its temperature. And then plus Q to cool the aluminum all add up to 0. All right. In an insulated system, we assume that the net heat comes from all the objects and is transferred between the objects and not to the environment. So you could rearrange this. You could say Q melt ice plus Q warm water is the opposite of Q to cool the aluminum, right? The heat that is used to melt the ice and warm the water is lost from the aluminum. Now, remember that Q's can be positive or negative. We're expecting this one should be positive. It takes positive heat to melt ice and to warm water. We need negative heat to cool the aluminum, and so this minus with a minus will actually make sense. Other people will just slap absolute values on this side and that side, and that works fine too. But I like to keep track of the minus signs because that's an additional check on my answer. I'm expecting delta T for the aluminum should be negative. All right? And I'm going to keep stirring this a little bit. Hopefully that was enough aluminum to melt the ice. I didn't think about that. Hopefully it will be. All right. So in this case, okay, yeah. All right, let's start with this equation. Now I'm going to move it up. If this is all you needed to get going, pause the video and proceed. Otherwise, I'm going to help you out. All right, so I'm going to move this up just so I have room. All right, I'm going to proceed with the solution in 3, 2, 1. Okay, to melt the ice, I'm going to say that's plus mass of the ice, latent heat of fusion for ice and water. I'm using the plus sign because it's a positive heat. If I was freezing the ice, I would use a minus sign. All right? For the warming the water, that's going to be the mass of the ice plus the mass of the water. Because remember, all this ice is going to melt and turn into water. So that's going to be a small correction times C of water times delta T of water. And then to cool the aluminum, there's this minus sign. Mass of the aluminum, C of the aluminum, delta T of the aluminum. Now, this looks at first like we have a bunch of numbers here. Number, 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 don't know it. Number, number, don't know it. It looks like we have one equation and two unknowns. However, remember both of these are going to the same final temperature. This is T final minus T initial of the water. And this one here is going to be T final minus T initial of the aluminum. All right, stirring this thing. Is it reaching an equilibrium temperature here? All right, just looking. It looks like this is stabilizing at about 9.2, which is probably way different, by the way. So T experiment looks like it's 9.2. This is plus or minus at least 2 degrees Celsius. All right, so let's just say 9. And I'll say, we'll discuss this later. I'm just finding that number. Oh, you know what? I'll show you too. Trying to stir it. So hopefully you can see that that's about the number I'm getting. You'll notice there's a tiny fleck of ice left, but essentially all the ice is melted and we're at 9.2. All right, so that's just the experiment. Let's go back to the board. So let's see if that's the number we actually get. I have a feeling it's going to be way off, and then we'll discuss why in the real life. All right, so now in this case, they have the same T final because they reach thermal equilibrium. So at this point, you can start cranking through this. I'm going to start to do the algebra here. I want to solve for TF. So MI LF of I, I'm going to start shortening the subscripts, plus MI plus MW times CW times TF minus MI plus MW CW T initial W equals negative MA CA T final A plus MA CA T initial A. And if you think you could do all the algebra, you might skip forward in a few seconds to just get to the end. If you think you could do all this algebra, skip ahead. I'm going to keep grinding away here, so I'm just shortening the subscripts. So I'm going to get all the T finals on this side. Oh, whoops. Remember, T final for the aluminum and the water should be the same, so I don't need different subscripts for the T final. That's the trick here. So moving all that stuff to here, I get M initial, M water, times C water, plus MACA, all that, times T final. So that's moving this term over here. Now I'm going to move all the other terms to the other side. MACA T initial A plus M initial, or M ice plus M water times C water times T initial water. Oh, there's this term, minus the energy to melt the ice. Okay, let's make sure I got this right. This one comes over and becomes positive. This one was over there and was positive. This one comes over and becomes negative. This one came over to this side and became positive, and I factored out the TF. So at this point, I can divide through, and what do I get? M initial plus MW times CW plus MACA. Now, I'm going to go ahead and start calculating here. It's going to take me a minute. I'll race you. So let's see what we get, and then we'll talk about real life. Okay, so mass of the aluminum was 100 grams. Oh, crap! Look at this. Look at the units. Kilograms. Kilograms. And look at this one. Kilograms and kilojoules. I'm going to put a 10 to the 3 up there to get rid of that. So if I use, ooh, interesting. However, look at this. If I use all the masses in grams, the units should drop out. And if I use all the C's in units of joules per kilogram per degree Celsius, And if I use this one in joules per kilogram, the joules and the kilogram will also drop out. Now you might notice this one has a T in it, but this one doesn't, right? So, aha, but we'll have a per Celsius that comes up here to the top from these units. So if I'm basically doing the unit check right now and I can see that it works, but just so that I don't get confused, I'm just gonna do everything in kilograms and joules, all right? And again, the grams would work out, so you don't have to do that, but I am gonna change this to 0.100 kilograms, and that means this would be 0.0121 kilograms, etc., etc. All right, so I'm gonna start doing the math. Sorry I didn't pre-calculate this one. It's a boring video, you can skip to the end. So the mass of aluminum was 0.1 times C of aluminum, which is 900, times temperature initial of aluminum, which was 100 as well. So I'm just gonna write these in as I go. That's 9,000. Okay, 0.0121 plus 0.3897 should be about 400. Okay, that's this term. Times CW, which is 4186. If you're wondering, hey, my teacher uses 4184 or 4187. Yeah, every book's a little bit different. Every C is a little bit different in every temperature range, whatever. This only gets us approximately right. Okay, times temperature initial of the water. What was the temperature initial of the water? Ice water bath. What's T initial? 0 degrees Celsius. We were assuming that. And when I was stirring it, I got down to about 2, and yeah, so whatever. That was correct within the error range of the thermometer. So let's see. Oh, okay. Now, I should mention this. Do I have to use Kelvin or Celsius here? Because these equations were originally defined as delta T's, it's okay to use Celsius everywhere, which means this one drops out. That's pretty cool. Okay, mass of the ice, right? So normally if you're using temperature like PV equals nRT, you have to use kelvins, but because this came from Q equals MC delta T, we can use Celsius everywhere. All right, so what's that last term? M ice 0.0121 times, what was it? 334 E3. So that's 4,000. 4,041. Let's get these numbers on the basement. So what was this? 389.7 plus 12.1, divide that by 1,000, times CW, 4186, that's 1681, and then mass of the aluminum, that was 0.1 times C of the aluminum, which was 900, that should be just 90. All right, so now when I do this, I get 9,000 minus 4,041. And I gotta divide that all by 1681 plus 90. 2.8 degrees Celsius. Notice this is way off from what we observed. We observed about 9 degrees, not plus or minus 2. What are some reasons these never quite match up? Let's go to the actual equipment and look. We can say it's in the right ballpark. We were expecting a 3-degree final temperature and we observed 9. So notice it is cooler than room temperature. So here's some issues that happen. In particular, this is probably what happened. We found an experimental result which is higher than what we expected. What's happening here is when I drop this piece of aluminum into this pot of boiling water, it's making good contact with the bottom of the pot, which is right next to the heat source. So it's quite possible that this was warmer than 100 degrees C when I dropped it in there. Some other issues that happen. What if I take this water and it's boiling hot and I pour it into this coffee cup like this, right? Right? And now, I have to throw this in here. It's not boiling. But the idea is if I take a piece of aluminum and drop it into here instead, it would probably be a little bit lower than 100 degrees Celsius, right? Because this is losing energy to the air, right? Also, what about the glass vessel itself? This isn't very well insulated. It's easy for this thing to lose thermal energy to the air or through the sidewalls. You got to heat up the container. So in practice, these numbers will never match up. A lot of times when you do this in lab, if you're not careful, if you have the piece of metal touching the hot plate itself, you're going to get artificially high values for T final. Whereas in almost every other case, if you drop it into some boiling water like this and then transfer it over, you're probably going to see artificially low measurements because so much heat is being lost to the air, and we didn't account for that in our equations. One more time on that on the board. Whoops. Sorry, it's a long video. Come on. Notice we didn't account for any loss to the container or the air, right? If you do that, the aluminum might cool down more. All right, so also, one of the things that can happen is, what if I had gotten a negative number for T final here? What does that mean? Well, you can't cool the aluminum below the temperature of the ice water. That doesn't make sense. That would mean that not all of the water, not all of the ice melted. So let's say you do this whole problem and you get a nonsensical answer here that says you get a negative T final. What that means is, oh, go back, redo the problem without this term, and just assume some of the ice melts, but not all of it. And then in that case, you'd get a different number, right, which should raise this up a little bit. All right, and so I think that's good enough on that one. Some tricky spots in there when you're actually doing the problem, especially the Celsius, the kilograms, whether you can use them or not, etc.